Hello everybody, Bryson, Adam, Chris, and I will be presenting our design of a solar power charging station for e-bikes. In today's society, demand for alternative methods of transportation to reduce one's carbon footprint is at an all-time high. E-bikes are a fantastic example of an environmentally friendly, convenient, and healthy alternative to other commonplace commuting methods. However, a major drawback to e-bikes is their expense. A way of mitigating this problem is by introducing sharing programs in order to reduce expenditures. Also, in a further effort to lower the environmental impact, off-grid power generation methods can be paired with charging stations. This includes the use of renewables, such as solar panels, to provide the necessary power for the e-bikes.
The goal of the projects is to design the power system and controls to optimally transfer power from a solar panel to an e-bike battery. The design will include the physical structure of the e-bike rack, as well as the user interface and locking capabilities. The bike rack unit will be self-sufficient without grid connection for full functionality and reliability, and the design will be powered by the built-in solar panel, and it must have a rechargeable storage system to act as an intermediate step in the charging process. Now, in order to successfully achieve the project objectives, first, power transfer will be safe, efficient, and will not impact battery health. Second, overcharging and over-discharging of the batteries will be prevented. Third, locking mechanism will be functional and secure. And fourth, design will require 2 microcontrollers. Now, in order to effectively manage the different systems involved in the overall design, 3 subsystems were established. First system is the power transfer and storage. The power is generated from the solar panel and must be transferred to a storage battery. Then the power must be transferred to the e-bike battery once docked. Also, to maintain battery health in the storage system, the input received from the solar panel must be regulated. Thus, with both the solar panel and energy systems operating on DC power, an appropriate DC-DC converter must be used to regulate the voltage to meet battery specifications. In addition, temperature regulation was crucial to maintain for the long-term system storage functionality. And with the temperature must be within the 18 to 22 degrees Celsius to maintain system health. Now, the second system is user interface, which takes care of the communication with the user. That includes the process in which the randomized code to unlock the bike is created and sent to the user. And also, one-time purchase is basically done through an online transaction website, such as Shopify, which takes care of the verification and the processing banking transaction for bike rack use. And then once verified, a code will be sent to the user to unlock the bike. Third system is locking mechanism. This system's objective is to tackle and eliminate one of the main issues with bike racks, which is safety. Our charging station is made for electrical bikes, which are quite expensive. Therefore, security of the bikes and ensuring that it will not be hijacked will satisfy any customer that uses our station.
After determining the main project objectives and some general concepts, we decided to split the project up into a few major subtasks. We designated 2 people for each subtask, both for the diversity of ideas in generating solutions and to prevent anyone from feeling overwhelmed by a particular task. The first subtask is the power transfer system, which Chris and I were responsible for. Next is the user interface and the system security side, which Adam and Nick focused on. And lastly, the battery management system, which was divided into the temperature regulation and charge control components, which were dealt with separately. For early stage testing, some of the design concepts, we used MicroCap software. This allowed us to simulate circuit operation for our solar panel in conjunction with the DC conversion circuit and storage batteries. Also, since the group already had access to the Arduino microcontroller, we used an Arduino Uno board along with a simple breadboard to test the individual sensors we used, along with the keypad and locking components within the user interface portion of the project. Pictured here is the overall prototype. To reiterate a little bit from our demonstration video, we have the power transfer system, which is comprised of a 40-watt solar panel, a buck converter circuit, 2 car batteries to simulate the energy storage and e-bike batteries, several voltage and current sensors, 2 relays, and 2 charge controllers. The buck converter uses a dual MOSFET configuration with PWM gate signals to control the voltage step down. In the Arduino code, the voltage readings from the sensors are used to determine the appropriate duty cycle ensuring the desired roughly 14 to 14.5 volts is seen entering the energy storage battery. The relays are used to control the connections between the solar panel and energy storage battery, and between the energy storage and e-bike batteries. And lastly, the two charge controllers are used to prevent overcharging of the batteries. With regards to the user interface and security, we utilized a solenoid lock, Bluetooth module, LCD screen, and keypad. The solenoid was self-locking, allowing the user to simply push the bike into the bike rack to lock it. To simulate a transaction, the Bluetooth module was then used to facilitate communication between the user and the bike rack. A randomly generated code was sent to the user's phone via Bluetooth, which the user could then enter into the keypad based on a prompt from the LCD screen. And if the code that was entered was correct, the rack would unlock the bike. Lastly, a temperature sensor was used to monitor the internal temperature of the bike rack. And if the measured temperature was above a preset threshold, the Arduino code would initiate the startup of a fan to help ventilate the unit.
In testing the final prototype, the several components that we used warranted a variety of testing strategies. The buck converter was designed to receive PWM signals from the Arduino to step down the voltage from the solar panel. The control system parameters were determined experimentally to ensure that we had acceptable characteristics. The relay logic also required extensive testing to ensure that all possible scenarios were covered. They operated based on inputs from the sensors, which determined when the e-bike battery was connected and disconnected. The lock mechanism utilized a simple mechanical latch to ensure that no user interaction was required. And then the charge controllers were purchased off the shelf and were tested as part of the whole design. They operated as expected. Finally, we had to use the breadboard and the Arduino to test the individual sensors, which we verified with a multimeter, in addition to generating random codes and testing that interaction with the Bluetooth module and the user's cell phone. Also, the unlock mechanism and the fan required 12 volts from the storage system, so we needed to incorporate some additional relays to control those connections. As for the major differences between our prototype and final design, the final design is going to incorporate larger lithium-ion batteries as we would find in a real e-bike. Because of this, the solar panel of larger size and output capability would be required. From a user interface standpoint, we'd incorporate a web domain such as Shopify for security measures, and additionally we'll incorporate a secure payment processing application to activate the unlock system. As for future developments of the design, we had initially considered incorporating wireless charging, but we later determined that it would be beyond the scope of our capabilities. This could certainly be added in the future. Also, designing the units in a more modular nature would allow multiple racks to work together and ensure that storage is more efficient. Next, we would incorporate MPPT controllers to maximize efficiency from the solar panel. And finally, we would prefer to use our own payment processing interface, such as an app or a website, and implement QR codes so that a user can easily access a particular rack.
As far as bumps along the road, the first major hurdle that we encountered was the miscalculation regarding the gauge of wire. Initially, the circuit for the power generation was constructed with 22 gauge wire. Parts of the breadboard and wire heated up to a point where the connections were melted, which was due to the current draw being too great for the gauge of wire. In addition to this, due to the prototype being built for temporary use, we ran into some issues with transportation of the unit. In doing so, the components bounced around, causing the connections to come loose or disconnect. Next, there were issues relating to the traces on the PCB board. During soldering, one of the traces melted, which caused the pin to be disconnected. Lastly, we encountered some issues relating to components. Specifically, the temperature sensor was not working, which we later found out to be a direct result of faulty components, which were shorting out the Arduino microcontroller and causing further issues. Based off the previously discussed problems, there were many lessons learned along the path to completion. First off, we learned that the wire gauge calculations need to be done prior to testing. If this was done, we would have discovered that 18 gauge wire was needed opposed to the 22 gauge wire, which would eliminate the frying of components. Furthermore, we also learned that components needed to be mounted permanently. This would have made testing and troubleshooting run a lot smoother, which would have saved a large amount of time. Next, we discovered that it would be very beneficial to include extra test pads on PCB boards. As we are not expert solderers at this point of time, accounting for some error in this stage of the production would be very beneficial. Lastly, we learned the value of keeping extra components on hand. Due to the nature of electronics, you're bound to come across some faulty components, so being prepared for that ahead of time can go a long way. That concludes our presentation, and thanks for watching. We will now take questions.